So I want to introduce what we're going to be thinking about in section 4.2 of the book, but as always, I want to introduce it thinking from the very start about why would we want to introduce this mathematics. This is a memo that we handed out very first, or we looked at in the very first couple of days with lots of different questions about a wind turbine that we might want to answer. And I want to actually jump over to 5. The order's a little bit weird because we're actually going to do this very early on. And it says, when the blades undergo maintenance and a worker is the tip of a blade that is stuck at a certain angle, how high is he above the ground? How far is he from the support shaft? And some other stuff about the slope and the angle. And so I just want to think about that question. And this is a question about something that moves in a circle, the blades, the rotor blades of a wind turbine. And we know something about the angle that they're at, and we want to know something about the position of the tip of the blade. So let's look at a picture, a very schematic picture of that. We've got something moving in a circle, and let's set it up in a coordinate system with the origin at the natural place at the center of the circle. And we know something about an angle, and let's say what we're going to do, as we did in the section 4.1, we're going to measure those angles whenever possible from the positive x-axis. And we might need to do something different in a particular application, but we're going to have this be our standard that we're going to start with. And given this angle, can we figure out where this point is? Well, we obviously need to know the radius of the circle, because that's going to influence how far it is from the y-axis, the x-axis, everything about its coordinates. So let's start out, to make things simple, just to analyze the pure mathematical case. Let's think about the simplest non-zero number, the simplest radius a circle could have in 1. Okay, so that's going to be the unit circle. And of course, we're going to have to scale things up whenever we do a real circle, but it's a good thing to start with. And the scale up will not be too hard. Well, it won't be hard at all. Okay, so here's the problem. Have that angle theta, and I want to find the x and y coordinates of this point. Well, this is x and this is y. We can drop a perpendicular here to make a right triangle, and voila, we're back in the situation of a right triangle and proportions in a right triangle. And so that's something where you have had an introduction to the basic trig functions in that setting. And they work on the circle simply because for any point anywhere in the xy plane, if you drop x and y, if you drop perpendiculars to find coordinates, you're built a right triangle. And if you know that it's on a certain circle with a certain radius, then you know the hypotenuse of that right triangle as well. And in this case, we're going to be real simple to start out with and assume that that's equal to 1. Okay. Now, there's another way the book talks about it. The book postpones talking about it in terms of this angle. They talk about this in 4.2, but they don't focus on it. They focus on that you might have gotten there, and this is really more realistic almost for the wind turbine. The wind turbine maybe started with the tip of the rotor blade out here, and then it cranked a certain amount over, and so it did a certain amount of arc length to get to this point. They say it in a rather artificial mathematical way. It's kind of weird. They say take the real number line and wrap it around the circle, which is kind of cool, and we'll maybe demonstrate that with tape measures and things like that. And so they want a letter for this, and I think it's a little bit unnecessary, but they call this letter T. Okay. There's really sort of 3 letters that we could attach to it, and again, I don't think it's super necessary for the book to use all 3. We've been calling this S for the arc length. This is really what we were calling when we think about S equals R theta. S is the arc length. And so you should think about the T as just being a special version of S where the radius is equal to 1. Okay, but otherwise they're essentially playing the same role. So I walk a certain amount along the unit circle. They're calling that T. And how does that relate to theta? Well, remember, with radians, if we measure everything with radians, and here's another good reason for using radians, we have S equals R theta. Well, in the case where R equals 1, we're calling ST, and they're just the same thing. Okay, so T and S and theta are all different names for the same thing. I apologize for that. But they're just sort of different perspectives. S we want to think of as arc length on a general circle. Theta we want to focus on this angle inside. T we want to think about as arc length on the unit circle. Well, if we use radians, they're all the same thing. Okay, so now let's actually figure out an example of this. It's getting a little cluttered. Okay, so suppose this angle were 30 degrees. Or in other words, that the angle in radians, or in other words, the arc length along the circle, given it's a unit circle, is pi over 6. And we're going to keep practicing that kind of translation, okay, and memorizing it as well. And we want to get our x and y. Ooh, that's silly. X and y. Okay. Well, this is a 30, 60, 90 triangle. So this is something that is from very basic geometry. Okay. Here, x is going to be, let's see, the ratios in a 30, 60, 90 triangle are, if that's 1, that's 1/2. And this is root 3 over 2. And if that's not, doesn't come in immediately to mind, well, you're going to have to memorize it. And we might also think about in class, where does that come from? Let's remember it. It's really a cool thing to rederive. Okay, so that tells us that at least for certain special angles, I can take the angle, and yes, I can get x and y. Okay, and what are these called? Okay, what we've really got is, in principle, a procedure that takes any angle, that's an input, theta or t, and we're creating the x and y as functions of that number. Okay, so that's a really profound thing. X here is called cosine of t, and y is the sine of t. Okay. And so in this perspective, and it's a little bit different from the triangle trig perspective, but we can answer it using the triangle trig ideas. You take a certain distance along the circle, you find that particular point along the circle, and then the x coordinate of that point is the cosine. The y coordinate of the point is the sine. One reason why that's a little different and a little bit more general than what we do with right triangles is it allows us to go all the way around the circle. As you go from a acute triangle to like an obtuse angle here to way around past 180, past 360, all the way around and around and around and around. These are always well defined. You just walk that much on the unit circle and then boom, where do you end up? And figure out your x and y coordinates. And so this means that it's well defined for anything. That's one reason I think they don't use theta here, just to make clear it's any real number. Okay, and we'll relate this to triangle trig as well, for no matter what quadrant we're in, no matter how many times we're going around the circle, in very soon, maybe in the next video. Okay, so we would say, expressing this fact about the 30, 60, 90 triangle, we would say that the cosine of pi over 6, or the cosine of 30 degrees, is root 3 over 2, and the sine of pi over 6, or the sine of 30 degrees, is 1/2. Okay, and another example that comes from our knowledge of special right triangles from geometry. What if this is a 45-degree angle? So this is going to be cosine t, that's sine t, this length here is t, and that's really just the same as theta if we use radians. It's exactly the same number, but it's the same concept no matter what units we use. Okay, so if that's 45 degrees, I thought it's showing up well. It's showing up okay. Alrighty, so the cosine of 45 degrees, and now what is that in radians? You should pause if you don't immediately know it. You really should pause and say, and remember, what is that in radians? Pi over 4. Okay, what is this? Well, this is a 45, 45, 90 triangle. Okay, and we know from special right triangles that that's going to be root 2 over 2. Or 1 over root 2. I'm not a huge stickler for rationalizing denominators. I don't think it's illegal to write 1 over root 2, but you should know how to rewrite it in this way as well. And the cool thing is that it's an isosceles triangle. These sides are equal, okay, because all these angles are both 45. And so that's the same thing as sine pi over 4, or the sine of 45 degrees. Okay. So we're going to, in the book, they have lots more examples of going all the way around the unit circle and trying to figure out, for especially very special angles, what the sine and cosine are. But in principle, no matter how far you are around, we could get the x and y coordinate. Now, we're not sure exactly how to do that for a complicated angle, but for example, if you have a calculator, or I'm just going to use my computer algebra system here, let's see, untitled, that sounds good. Okay, like sine pi over 3, it does that. Okay, let's see if it does that for real. Yeah, root 3 over 2. So it turns out that sine pi over 3, that's a 60-degree angle. That's this number that we've seen as a cosine before. Okay, but a calculator will give you, for example, sine. I don't need to display this. Sine of 1 radian, for example, not 1 degree. Oh, it needs numerical analysis. It needs to, I'm going to evaluate numerically. There you go, 0.84147. And that's 1 radian is around right up here. Okay. You could do the cosine of 15.2. It totally makes sense. Go 15.2 radians around the unit circle. Where are you? Minus 8.7374. Okay. So that's a good intro. The book has some other good information, and we're going to jump into this. But remember, what we're really interested in is questions like this, where we're going to use that to model some actual physical situation.